Today we're going to talk about a special case of the application of the equilibrium theorem and the principle of indifference that we talked about in the last series of lectures. That special case will be when we have the matrix for our two-player zero-sum game, a square matrix, n by n, and we're only going to look at it here in the case where that matrix happens to be non-singular. You can think of that as determinant, which is not equal to 0, or we're going to certainly need to use the fact that a non-singular matrix has an inverse. Also, we're going to only look at the special case when the game is an all strategies active game. What does all strategies active mean? That means that there have to exist optimal strategies for both sides. There have to exist optimal strategies for both sides, in which the probability for each pure strategy, for each individual strategy, is positive. So there are no eliminated strategies, no strategies which get ignored in optimal strategies for each player. Now that's a lot to assume, and certainly not every game is like that. But if we're so lucky as to have all those situations occur, and there are a wide class of games in which they do occur, then we can simplify things and use the notation of linear algebra to get a nice compact form of solutions for the game. And so we're going to run through how that works. We start by talking about strategy vectors, optimal strategy vectors, P for player 1 and Q for player 2. Now I'll remind you one more time here, our author in the version that I'm looking at, and I believe most of you have, uses row vectors for P and Q. In some other versions of the book, he uses column vectors for P and Q. If he uses column vectors for P and Q, just replace everything I have here by using P transpose instead of P, because the transpose of that column vector would turn into a row vector like what we have here. So say we have optimal strategies P and Q, P for player 1 and Q for player 2. This would be for player 2. And the value of the game V. What characterizes those optimal strategies and value? Well, we've seen under all the conditions that we have in all strategies active game that by the principle of indifference and the equilibrium theorem, that the sum from I equals 1 to n of P sub I aij will equal V for all j. What does this mean? Well, this quantity here is the expected return for if player 1 plays this optimal strategy given by the vector P, and player 2 plays, say, a particular column J. And so for each choice of J equals 1 to n, these are the different choices of the columns for player 2. Player 1 expects the exact same thing. That's this principle of indifference here, the exact same thing, the value of the game V, as the return. And similarly, player 2 expects this amount if player 1 chooses column 1, and that's assuming player 2 plays this optimal strategy Q. If player 2 plays player 1 plays row I should have said. So let me say that again. This is the expected return if player 1 plays row I and player 2 plays the optimal strategy Q. Again, the expected return will be exactly V, no matter which row, I equals 1, 2, 3 up to n, player 1 plays. So again, I've shown you here, I've just put this for reference, our matrix A, and we're going to need one little nice notational thing. If we take A and multiply by Q, we get this column vector V, 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 all the way up to V, all V's, a column vector, a 1 by n, n by 1 column vector with all V's. Why is that? That's exactly what we get here. This is just, this quantity on the left is precisely the matrix A multiplied by this is the the ith entry. This is the ith entry in the column vector you get by taking A and multiplying it by Q. In a similar way, this quantity above here is exactly the jth entry in what you get when you take the row vector P. That should be. So now we get A times Q. In fact, I want here Q transpose. Q transpose will be a column vector. That's n by 1. A times Q transpose will be this column vector, each of whose entries is V. And that we can write as V times the vector 1, where here we're going to write the vector 1, which we show as, when we write it, we'll write it like this. 1 with the vector hat, that will be this boldface 1 there. That will represent the column vector, which is an n by 1 vector with all 1s. So A times Q transpose will be V times 1, which means this column vector with all V's. That's what the previous line tells us. And thus, I'm sorry, I have to change these to Q transposes because these are going to be column vectors. V transpose, when I just multiply both sides by A inverse, I multiply by A inverse and V is just a constant, so I can pull it out. V times A inverse times 1. Here I can just manipulate that a little bit and get that the number 1, which is 1 transpose times Q transpose. What is 1 transpose times Q transpose? 1 transpose is this vector 1, 1, 1, etc. Q transpose is this vector Q1, Q2, up to Qn. So this product, 1 transpose times Q transpose, is just the dot product of these two vectors, which is Q1 plus Q2 up to Qn, which is just the number 1 because this vector Q is a probability vector and the sum of the entries have to be 1. So that number 1, when I put in what Q transpose is above, is just V times, is just 1 transpose times this vector, V A inverse 1, which is V times 1 transpose A inverse 1. And we can then divide by this quantity here, which is just a number. Remember, 1 transpose A inverse 1 is a 1 by n vector times an n by n matrix times an n by 1 vector. So it just ends up being a 1 by 1 matrix, or a number. It can't be the number 0 since 1 is equal to the value of the game V times that number, so we can divide by it and get a formula for the value of the game here, which is 1 over 1 transpose. That's this row vector times A inverse. Remember, A is non-singular, so it has an inverse, times 1. And again, remember that this quantity here can never be 0. This is, again, as long as A is invertible, so that makes sense. Then we get Q transpose is equal to A inverse times 1, that's this thing here, times V, and V is just this quantity 1 over that denominator. So just from here, we get a formula for Q transpose. Remember, Q transpose is this column vector Q1, Q2, up to Qn. That tells you player 2's optimal strategy. Now, I'll remind you the results tell us, in this special case, the value of the game V is just this quantity we talked about before, 1 over this 1 transpose A inverse 1. That's the optimal strategy for player 2 is this column is written by this column vector where Q transpose is this. If you want the row vector, you just take the transpose of this quantity. And in a similar way, again, I have to fix this. We have the row vector P, which is player 1's optimal strategy, will just be 1 transpose A inverse over the same quantity. I haven't derived this, it's derived exactly as we did before. And I should notice these are slightly different from the way it is in the book. If you check it in in the PDF file that most of you are using, they had been assuming that P and Q are row vectors, which I've been trying to keep consistent now, which is why I had to change everything to the way I've written it right now, with Q transpose given by this, and P, the optimal strategy for player one, the row vector P given by this. The author seems in this particular version to kind of interchange them in this one section, to use column vectors instead of row vectors. But remember, in all of this here, the vector P is this vector P1, P2 through Pn. The vector Q is Q1 through Qn. And you can see this formula will give you a column vector. A inverse times the column vector 1 will be a column vector, and this denominator is just a constant. And similarly, 1 transpose times A inverse will give you a row vector, and you're just dividing it by a constant there. So these three formulas for V, for Q transpose, and for P will completely solve a game under this rather large list of hypotheses that we mentioned before, which I'll remind you were that the game must be an all strategies active game. That means no zeros in these optimal strategy vectors. And the matrix A of the game, of course, must be a square matrix and be a non-singular matrix. Let's look at one example using the formulas from before. Let's say we have a game matrix that looks like this. This is a non-singular matrix. In fact, you can compute easily the determinant of this matrix is 14, which confirms it's non-singular. And of course, you can compute its inverse. I won't show you that here. I just had my computer algebra program do that, but I'm sure you could all compute the inverse of the matrix A entirely by hand if you needed to. Then we can look at the matrix product here. 1 transpose A inverse times 1, that's the one vector, the transpose of the one vector, so you get a row of ones, times the matrix A inverse times the column vector, 1, 1, 1. And again, that's a simple computation you can do with your computer algebra program, or this one's very easy to do by hand, and you get the number 3/2. The value of the game, which is just the reciprocal of this quantity, will then be 2/3. So we've determined just by these simple formulas that this is a game whose value is 2/3. If you want to know optimal strategies, you can compute that the row vector P, I should have left that just as P there. P is 1 transpose times A inverse over 1 transpose A inverse 1. In other words, it's just 1 over the value. It's just the value of the game times this matrix, 1 transpose A inverse. The value of the game is 2/3. And we then do this, look at this matrix product. And again, that's very easy to compute. And you get the row vector 1/3, 1/3, 1/3. And the formulas tell us that Q transpose is actually given by A inverse times 1 times the value of the game V, which is 1 over 1 transpose A inverse 1. So again, the value of the game 2/3, and we take A inverse times the 1 vector, 1, 1, 1, and we get the vector 1/3, 1/3, 1/3. In other words, Q will be 1/3, 1/3, 1/3, like that. Now, these are optimal strategies. It kind of should have been obvious right from the beginning that these are the optimal strategies. This is something we're going to be discussing later this week. When you look at this matrix A, you see that the different rows and the different columns all have a similarity. They're just these same numbers, 2, 1, and -1 permuted. They all function the same. There's a symmetry among the choices. And because of this symmetry among the choices, it's natural to expect that an optimal strategy will play each choice with equal probability, and that's what we see here for both players P and Q. So this is a game that's favorable to player one. It has a value of 2/3, and because of the symmetries, or because of these simple calculations we just went through, we can see that the optimal strategies are 1/3, 1/3, 1/3 for, in this case, each of the players.